Hello, my name is Dave Oliver. I'm the Chief Technology Officer for the Probitas Project. Our company focuses on developing efficient and effective solutions using our expertise across radar, sonar, and sensor processing domains. Today, I'm going to go over our work with IWS-2 above water sensors, where we're applying data science and adaptive algorithms to radar signal processing. While our target for this project covers radar-centric challenges such as detection, tracking, and classification, we have also been successful in using these techniques in other areas, such as gamma ray spectroscopy, a completely different field. We hope you find this brief informative, and you can see how our strength in data engineering and science can apply to other areas. The Probitas Project was founded with a goal of solving challenging problems. In Latin, Probitas stands for honesty and uprightness. This is our main goal, being true to our customers' needs and developing trust and confidence with our partners. We maintain expertise in radar, digital signal processing, real-time software development, machine learning, and artificial intelligence. Our employees have background in program management, test and evaluation, system development, radar, and nuclear physics. In the past few years, I led the development of software for the Virginia-class submarine radar, as well as hardware, software, and combat system interfaces for the next generation surface search radar. That leads me to this project, where we start with a sensor that provides high velocity and high volume data. Petabytes of data is being collected with just a single sensor in operation. We're going to talk about how we are set up to address this problem. This topic is broadly listed as adaptive algorithms, but it is better to think about the challenges and how innovation can bring about disruptive change. In the case of IWS-2, the program office has a challenging program to rapidly deploy a new radar to nearly all surface combatants. The sensor is capable of performing the anti-submarine warfare mission by providing periscope detection and discrimination. That is, identifying real targets embedded in dense clutter. However, capability and utility intersect when we talk about the need for automation. The operational needs for signal processing and ASW capability improvement were defined by the Navy. The Navy has made large investments in this area over the past few decades. However, even with all of this investment, there is still a requirement for an attentive operator. And with that operator, you also have to provide initial training, 24/7 watch standing, and recurring training. The question becomes, how can we reduce the reliance on a full-time operator by approaching the problem differently? Here's the solution we are working on. First, a data pipeline to process, train, and evaluate the data. Second, an architecture that provides continuous improvement. That is, as new data is collected, there is new information that can be used to improve the operational performance of the sensor. Finally, the algorithms themselves to perform high-stakes decision-making. We'll talk about what that means on the next slide. Classifying a periscope can be considered a high-stakes decision process, much as a self-driving car avoiding an accident. The stakes can include defensive maneuvers and offensive actions based on the operational footing. Our goal is to make an AI system that removes the operator. This provides mission enhancements through always attentive operation. In addition to the high stakes, the decisions occur frequently, many times per second, but with a very low probability of an actual periscope. Managing the weighting of the data used in classification is known as class imbalance and is a key challenge in this problem. On the right side, you can see an example of the explainable AI output. We develop unique visualization surfaces to provide information about the applicability domain. That is, how well the machine is expected to perform based on existing data. In this graph, we can see that there's a signal-to-noise ratio dependency, which is shown as the color differences. In addition, this visualization showed us that there is a separation of these blobs, and we were able to dive into data to figure out that that is actually an environmental difference based on the sensor's position when the data was collected. This was a surprising result to us. We're able to visually see where typical data is collected and where other data does not fit into the same applicability domain. We also highlight the traditional need for higher signal-to-noise ratios. Low SNR events are often the boundary of decision-making processes. These visualizations have led us to inform the machine about SNR to enhance the classification process in these low SNR regimes. These are the three focus areas we're developing in phase one. The algorithms expand upon traditional signal processing and move to a data science environment in the pipeline. A pipeline can be viewed as a key tool to processing, analyzing, and updating a machine learning system. We're designing our pipeline using commercial government cloud capabilities, providing cyber-secure and on-demand computing. These approaches can also be used at different classification levels. The pipeline enables the scaling and analysis of this data. Once the data is ready for processing, we're developing algorithms that apply to traditional sensor processing problems such as detection, tracking, and classification. An example classifier is shown in the image below. In this case, an autoencoder is used to perform unsupervised classification. This allows the computer to do the hard work of labeling data for us. We then use supervised techniques, incorporating Geographic Information System, GIS, and kinematic data for fine-tuning. Finally, we are addressing the high-stakes decision-making process. Is this a submarine or not? We're using explainable AI techniques to guide the methods and tools needed to make this decision. Our goals are high reward based. We show an estimate for the human power required with the current technology. Successful insertion of technology could have a high payoff for the Navy. We're progressing to large-scale data integration as it is available from the program. Here we show you an overview of the work being performed. Of importance to our customer is that there is a narrow window to avoid these training costs in their program. This includes developing schoolhouses, training curriculum, personnel processes, etc. We're very much interested in working towards advancing this approach to achieve long-term cost savings. I can also point to the flexibility of the tools and techniques. The data pipeline and the high-stakes decision-making tools are applicable to many other sensor classification problems. We can reuse much of this infrastructure for any DoD problem. To do so, it is important that we have sufficient data and an understanding of the current approaches and limitations. We'd be happy to talk more about those needs for any problems you are facing. The key challenges we are attacking are shown in the first column of this table. This is the baseline for the system and includes operational, schoolhouse, and single-shot training. In the middle column, we highlight the approach we are developing. I'd like to point to the key benefits to the fleet. That is, using computers for what they are good at. In theory, this lets the human focus on tactics and techniques. Finally, the significant benefits are shown in the third column. We highlight that there are significant operational personnel costs, ongoing training costs, and the benefits of the approach we are developing for managing large volumes of data can be applied elsewhere. Successful removal of an operator in the loop can save in excess of 100,000 human hours per year. I'd like to point out Probitas is an agile and efficient team with unique skills. We want to highlight that small teams can provide significant value to our customers. And in doing so, small investments such as this SBIR can result in large payoffs. As I mentioned, we are focused on a PEO IWS-2 development radar. However, we have a background in a variety of other sensor processing domains where techniques we develop can be applied. We note the challenges of high velocity and high volume data intersecting with the importance of decision making. Programs such as airborne submarine radar detection systems have direct and obvious applicability. But we also note that our capabilities can be applied to many other sonar, radar, and electronic warfare programs, which would include performing tasks under data analysis, reduction, and performance estimation. This also includes programs that are ready for test and evaluation, multi-sensor combination programs, i.e. data fusion, and problems where the size and velocity of incoming data are large, proportional to the resources available to analyze it. I want to update this slide and note that Probitas has received a GSA multiple award schedule. This is an easy to fund, task-based contract that can be used for follow-on phase 3 activities. We'd be happy to talk to you about this capability. This view of the data pipeline shows the broad capability Probitas is developing. We have expertise with multiple sensor types and in developing signal processing algorithms. We are implementing modern classification techniques and explainable AI algorithms for high-stakes applications. Our company is also working as an integrated member of test evaluation teams to analyze sensor data. We have developed capabilities in managing cloud resources, enabling cyber-secure remote access, and we have implemented innovative tools to access this data efficiently. Probitas has a goal of employee ownership. We believe this motivates everyone to work for the good of the customer and to challenge each other to achieve success. We're using state-of-the-practice technologies and inserting custom R&D as it's applied to DoD programs. Finally, I'd say we with this group of technologies, when taken together, has the potential to be disruptive. Success can provide monetary, personnel, and performance advantages. In this case, technology disruption has a potential for high rewards with a small investment to develop it. Thank you for listening in on this Tech Talk. We are the Probitas Project, located in Virginia, and our contact information is attached here. Please visit our website to learn more about our core capabilities. Once again, I'm Dave Oliver. Please feel free to reach out to me directly at my listed contact information. I'm happy to share more about this project and to see if there are areas where our expertise in signal processing, data science, and decision-making can be applied to your program. Thank you very much.